Okay, next one is number 23 on section 7.3. And what we're going to do is we're going to take the region bounded by the curve, the square root x equals the square root of 5 times y squared, x equals 0, y equals 1, y equals negative 1. And this is going to be this region. This is y equals 1, this is y equals negative 1. This is the line x equals 0, which is just the y-axis. And this is the curve x equals the square root of 5 times y squared. It's just a parabola, and it's positive, so it's open to the right. There's no shift, so the vertex is right there on the origin. And again, it's just by a factor of a square root of 5. We do have some symmetry, so we can use that to our advantage in a moment. So we're just going to use these horizontal discs because we're going to rotate it around the y-axis, about the y-axis, and this is the reflection. So it's what it looks like after 180 degrees. So we're just going to take these horizontal discs. Now the radius is what I need to find. So the radius of the disc is just given by the x value at any point on this curve as y goes up. So as y goes up, my x value goes out, and it's related by this equation, x equals the square root of 5 times y squared. So whatever y is, I can find that. When y is 1, x is going to be square root of 5. So we've got that, so we just go back over here to our general form. Volume equals the integral from negative 1 to 1 of pi r squared dy, but we do have symmetry, so we can change this from negative 1 to 1 to 0 to 1, and just double that. We'll take the pi out in front, and we've got our r squared dy. And then the radius as a function of y is the square root of 5 times y squared. I'm going to square that. Well, that works out pretty good because the square root of 5 squared is just 5, and then y squared squared is y to the 4th dy. And again, I still have the 2 pi in front. So I take the antiderivative. The antiderivative of y to the 4th is y to the 5th over 5. I have the 5 in front, so those cancel. And then if I substitute 1 in here, I just have 1 to the 5th. If I put 0 in here, I have 0, so that's not going to matter. That's just going to be minus 0. So 1 to the 5th is 1. 2 pi times 1 is 2 pi. So that was short and sweet. And then the next one, number 24. So we have here. Line this up. And again, we have the region bounded by these curves. Y equals, x equals y to the 3/2 power. X equals 0 and y equals 2. Now I remember this equation because we studied these a lot when we were talking about cusp and stuff. And x to the 2/3 y equals x to the 2/3 look like this. So I kind of just solved this for y just to get a quick idea of the sketch. And again, we have a parabola, half of a parabola opening to the right. Looks like that anyway, but it's actually this cusp. And then I rewrite it like this because I'm going to be revolving it around the y-axis, so I'm going to use horizontal disc, so I'll make sure that it's in terms of y, x in terms of y, so I can find my radius. And I'm going from x equals 0, so this is this axis. This is the line y equals 2, so this is my region, revolving that about the y-axis. And y equals 2, that kind of gives me my ending point. I know I'm going to start at 0, so I'm just going to integrate from 0 to 2. This is where the curve intersects. And that's no problem. So again, my radius is just given by y to the 2/3, y to the 3/2. That's my radius, y to the 3/2 power. That's the x value at any given y. So we go back over here and put it into our standard form, or general form for the volume. Using the disk method, these are still disks. These are horizontal disks. So the integral from 0 to 2 of pi r squared dy. And then I'll take the pi out in front, and I'll substitute for r, it's y to the 3/2 power, that's squared. And when I square y to the 3/2, I just get y cubed. Still have my pi in front, then I take the antiderivative of y cubed as y to the 4th over 4. And I evaluate that at 2 and 0. 2 to the 4th is 16. 16 over 4 is 4. So that's 4 pi. If I put 0 in here, I just get 0. So that's just 0. So I end up with 4 pi. So that wasn't too bad either.